Sometime in 2025, 4 astronauts will strap into a capsule on top of the most powerful rocket ever built and leave Earth. The mission is called Artemis II. Their trajectory will carry them around the moon, past the far side, the half that never faces our planet, and back. No landing, no surface samples, just a loop, a sling around the dark edge and home. It will be the first time human eyes have seen the far side of the moon since December of 1972, when the crew of Apollo 17 closed the hatch and never came back. 53 years, more than half a century of silence between human visits. During that silence, we sent robots, orbiters, landers, radar instruments, and laser altimeters and gamma-ray spectrometers. We mapped the moon down to the centimeter. We catalogued its craters, measured its gravity, sampled its dust. By every reasonable metric, the moon became the most studied object in the solar system. More data than we have for Mars. More data than we have for Venus, Jupiter, or Saturn. And here is the thing that nobody talks about in the press releases. The more data we collected, the less the moon made sense. Not in a trivial way. Not in the way that a puzzle has a few missing pieces. In the way that the pieces you already have do not fit each other. The moon you were taught about in school, the one that formed from a giant collision, cooled down, and became the dead grey rock in the sky. That moon does not match the data anymore. It matched in 1975. It matched in 1990. It stopped matching somewhere around 2010. And it has been getting worse every year since. The object you see from your window tonight is the most familiar thing in the night sky and simultaneously one of the least understood bodies in the solar system. Those two facts should not coexist, but they do. Everything humanity knew about the moon before October 7th, 1959, came from one hemisphere, one face. The same face, every night, for the entire history of human civilization. The moon is tidally locked to Earth. It rotates on its axis at exactly the same rate it orbits us, which means it permanently shows us one side and permanently hides the other. You have looked at the moon hundreds of times in your life, and you have only ever seen half of it. The other half was a blank page. Every astronomer before 1959 assumed that the blank page looked roughly like the front. Why would it not? It is the same object, the same rock, formed from the same event. So when the Soviet probe Lunar 3 swung behind the moon and sent back the first photographs of the far side, the expectation was simple. More of the same. More dark plains called Maria. More familiar basalt fields. More of the grey, flat landscape you can see with a cheap pair of binoculars on a clear night. What the photographs showed was something else. The far side had almost no Maria. Instead of flat dark plains, there were highlands. Cratered, rugged, mountainous terrain, dense and battered in a way the near side is not. It looked like a different world. Sergei Korolev, the chief designer of the Soviet space program, the man who had built the rocket that launched Lunar 3, saw the images before anyone else. Even through the grainy resolution, the contrast was obvious. Two hemispheres that did not match. At the time, scientists noted the difference and moved on. The cameras were crude. The data was thin. Everyone assumed that better instruments would smooth out the discrepancy. That the far side would eventually reveal itself as a mirror of the near side with minor variations. Better instruments arrived. The discrepancy did not smooth out. It deepened. In 2009, NASA sent the Lunar Reconnaissance Orbiter into a low polar orbit around the moon. On board was an instrument called LOLA, the Lunar Orbiter Laser Altimeter. For years, it fired millions of laser pulses at the surface below and timed how long each one took to bounce back. Centimeter-level precision. Every ridge, every crater, every basin. When the data came together, it produced the most detailed topographic map of any object in the solar system. More detailed than anything we have for Mars. More detailed than our own ocean floor. And this map confirmed what Lunar 3 had hinted at half a century earlier. Except now the numbers were exact and the numbers were disturbing. The crust on the near side, the half you see from your window, averages about 60 kilometers thick. 60 kilometers of rock between the surface and the mantle below. The far side averages close to 100 kilometers. In some regions, it pushes past 110. 40 to 50 kilometers of difference between two halves of the same body. If you picked up a basketball and discovered that one hemisphere of its shell was almost twice as thick as the other, you would not shrug and call it a quirk. You would hold it up and ask what happened to this thing. That is the moon. One face sits on a thin shell. The other is buried under a wall of rock nearly twice as deep. And the transition is not gradual. You do not slowly wade from thin to thick over thousands of kilometers. The boundary is relatively sharp. You cross from one structural regime to the other over a narrow band, as if someone drew a line and said, this side is built one way and this side is built another. 50 years of orbital data, dozens of missions, thousands of papers. Nobody can tell you why. The asymmetry is not on the surface, it is in the skeleton. So the next question follows on its own. If the two halves are built on different frames, are they at least made of the same material? They are not. In 1998, NASA launched a small, inexpensive spacecraft called Lunar Prospector into a low polar orbit. Its job was to sniff the moon's chemistry from above using a gamma-ray spectrometer, an instrument that detects the faint radiation emitted by elements in the top layer of soil. For 18 months it circled, recording the chemical fingerprint of every region below. When scientists processed the data, one result stood out above everything else. A group of elements with an ugly acronym, KREEP, potassium, rare earth elements, and phosphorus, was distributed across the moon in a pattern that made no geological sense. KREEP is not exotic. It is a byproduct of how molten rock crystallizes. When a body like the moon first forms, it is a ball of magma. As the magma cools, minerals solidify in a specific order. The last residue, the dregs at the bottom of the pot, is enriched in KREEP. It should be everywhere. It should be distributed more or less evenly through the crust, the way sediment settles evenly in a glass of muddy water. It is not. The data, mapped by Lawrence and his colleagues, showed that virtually all of the moon's KREEP is concentrated on the near side. The far side is almost clean. Two hemispheres of the same body, separated not just by a different crustal thickness, but by different chemical composition. One half got the residue, the other half did not. This is not a minor asymmetry. KREEP elements are radioactive. They generate heat. Their concentration on the near side means that for billions of years, one hemisphere has been warmer than the other from the inside out. The moon is not just shaped differently on each side, it is built from a different recipe. And no one can explain how a single cooling body, formed from a single event, managed to sort its chemistry into two separate drawers. There is one model that tries. In 2013, a team led by Mathieu Lanneville published a thermal evolution study that traced the consequences of the KREEP asymmetry forward in time. The logic was clean. If the near side has more radioactive elements, it stays hotter longer. A hotter interior means a thinner, weaker crust. A weaker crust is easier for magma to punch through. Magma reaches the surface, floods the lowlands, cools into dark basalt, and you get the Maria, the flat dark plains that make up the face you recognize when you look up at night. The model works. It explains the Maria. It explains why the far side, stripped of creep, stayed cold and rigid. Its thick crust sealing the interior shut like a vault door. It is an elegant piece of work. And it answers absolutely nothing. Because Lanneville's model starts after the asymmetry already exists. It tells you what happened once creep was concentrated on one side. It does not tell you how it got there. Think of it this way. You walk into a kitchen and the stove is on fire. Someone hands you a detailed simulation showing how grease ignited at 360 degrees, how the flame spread to the curtain, how the curtain lit the ceiling. Every step is modeled. Every temperature is accounted for. You nod along. It all makes sense. Then you ask the obvious question. Who turned on the stove? And nobody in the room has an answer. That is where lunar science stands with the KREEP problem. The fire is well understood. The ignition is not. Every model of the moon's thermal history is a story that starts in the middle. The first chapter, the one that explains why one hemisphere received nearly all of the radioactive seasoning and the other received almost none, has not been written. If the answer is not in the surface geology and not in the chemistry, then maybe it is deeper. Maybe the answer is buried under the crust, in the structure of the body itself. In 1968, two scientists at the Jet Propulsion Laboratory noticed something that should not have been there. Paul Muller and William Sjogren were tracking the orbits of Lunar Orbiter spacecraft as they circled the moon, measuring their velocity with extreme precision using radio signals bounced between the spacecraft and Earth. The velocity should have been smooth. A body with a uniform interior pulls on a satellite with a uniform force. The orbit should be predictable, clean, and boring. It was not. The orbiters were speeding up and slowing down in specific places. Over certain Maria, the spacecraft accelerated as if something beneath the surface was pulling them closer. Over other regions, they slowed. The accelerations were small but unmistakable, and they mapped onto specific locations with surgical precision. Muller and Sjogren called them mascons, short for mass concentrations. Buried under the basalt plains of the near side, hidden beneath kilometers of rock, were regions of anomalously dense material. Something heavier than the surrounding crust, something that the surface geology did not predict, was sitting down there pulling on everything that passed overhead. The discovery was a puzzle, but not yet a crisis. You could explain mascons if you tried. Maybe they were dense plugs of solidified magma. Maybe they were remnants of the impactors that carved the basins in the first place, chunks of iron-rich asteroid material that sank into the crust and stayed. The explanations were speculative, but they were plausible. The problem was that in 1968, the data was crude. The resolution was low. You could see the mascons, but you could not see their edges, their depth, their internal structure. You could not tell whether they were shallow features near the surface or deep anomalies reaching into the mantle. To answer that, you needed a better instrument. And when that better instrument finally arrived, 4 decades later, it did not simplify the picture. It shattered it. In September 2011, NASA launched 2 washing machine-sized spacecraft from Cape Canaveral. They were called Ebb and Flow. Together they formed the GRAIL mission, the Gravity Recovery and Interior Laboratory, led by Maria Zuber of MIT. The concept was deceptively simple. 2 probes fly in formation around the moon, one behind the other, separated by a precise distance. A microwave ranging system measures the gap between them with an accuracy of less than a micron, a fraction of the width of a human hair. When the lead probe passes over a region of higher density beneath the surface, gravity tugs it forward by a tiny amount and the gap between the 2 spacecraft changes. By tracking these changes over thousands of orbits, you build a gravity map of everything beneath the crust, not a surface map. A map of what is hidden below. GRAIL spent 9 months circling the moon at altitudes as low as 23 kilometers. By the time it was finished, the dataset it produced was the most precise gravitational map ever made of any body in the solar system, including Earth. For the first time, scientists could see the interior of the moon with the kind of resolution that geologists on Earth take for granted. And the expectation was reasonable. Better data should mean cleaner answers. When you upgrade from a blurry photograph to a high-definition scan, the shapes should become clearer. Edges should sharpen. Ambiguity should shrink. That is not what happened. The GRAIL data revealed more anomalies than the old data, not fewer. The mascons Muller and Sjogren had found in 1968 were confirmed, but they were only the beginning. Beneath the surface, the moon was riddled with density variations that no existing model had predicted. The gravity field was noisier, more complex, more structured than anyone expected. Maria Zuber had spent her career building instruments to answer questions about planetary interiors. GRAIL was supposed to be the instrument that closed the book on the moon's internal structure. Instead, it opened a new one. The data was better than ever. The understanding was worse than ever. And that paradox, more precision leading to less clarity, would become the defining pattern of everything that followed. The mascons at least had the decency to sit under recognizable features. They hid beneath Maria, beneath the dark basalt plains that you can see from Earth with your bare eyes. You could point at a spot on the moon and say there is a mascon under that sea, under that basin. The correlation was imperfect, but it was there. Then GRAIL found something that did not correlate with anything. In 2014, Jeffrey Andrews Hanna and his colleagues published an analysis of the GRAIL data that focused specifically on the far side. What they found were linear gravity anomalies, long narrow bands of elevated density running beneath the surface in geometric patterns. Not circular, not basin-shaped, linear, like buried walls. These structures had no visible expression on the surface. If you stood on the moon directly above one of them, you would see nothing unusual. Craters, dust, the same battered highland terrain that covers the rest of the far side. But beneath your feet, kilometers down, the density of the rock would be measurably different, arranged in a pattern that no random geological process easily explains. Andrews Hanna interpreted them as ancient igneous intrusions, magma that forced its way into fractures in the crust billions of years ago and solidified into dense vertical sheets. The interpretation is plausible. Magma does this on Earth. But on Earth, when you find intrusions like these, you also find surface evidence, volcanic vents, lava flows, dike swarms that reach the top. On the far side of the moon, the surface above these linear anomalies is silent. Whatever forced magma into the crust at these depths either did not have enough energy to breach the surface, or something about the far side's thick, rigid crust acted as a lid, sealing the evidence below. Either way, the result is the same. There is a geometry beneath the moon's skin that the skin itself does not acknowledge. A skeleton whose bones do not match the body. 3 datasets now. Crustal thickness from LRO. Chemistry from Lunar Prospector. Gravity from GRAIL. 3 independent instruments. 3 independent anomalies. Does any single model explain all 3 at once? No. And the failure is not for lack of trying. The most intuitive explanation for mascons is a model called mantle rebound, developed most thoroughly by J. Melosh. The idea is straightforward. A large asteroid hits the moon and excavates a basin. The impact removes a column of crustal material. The mantle, which is denser and sits below the crust, rises to fill the gap, the way water rises in a hole dug on a beach. As the mantle plug cools and contracts, it pulls surrounding material inward and creates a localized concentration of mass. A mascon. The physics is clean. The model reproduces the gravity signatures of some near-side basins reasonably well, but it does not explain the linear anomalies on the far side. Those structures are not circular. They are not basin-shaped. They did not form from impacts. Melosh's model has nothing to say about them. So you try another model. Superisostatic compensation. The idea here is that the moon's crust is not in gravitational equilibrium. Some regions carry more weight than they should, like a wooden board with a brick sitting on one end. The brick creates a gravity anomaly. The model can account for some of the linear structures, but it contradicts the crustal thickness data from LRO. If the far side crust is truly 100 kilometers thick and rigid, it should be strong enough to support these loads without deforming. But the gravity data shows deformation. The crust is behaving as if it is both rigid and weak at the same time, which is a contradiction no single thermal history can resolve. Every model that covers one anomaly exposes another. Every patch rips the fabric somewhere else. It is like fixing a leak in a boat by drilling a hole in the opposite wall. The surface does not add up. The subsurface does not add up. The models do not hold three variables at once. If the problem is not in the skin, and not in the bones beneath the skin, then maybe the problem goes all the way down. Maybe we do not understand how this body was born. There is an answer to that question. It has been the answer since 1984. In 1975, two planetary scientists named William Hartmann and Donald Davis published a paper proposing that the moon was born from violence. Their model said that roughly 4.5 billion years ago, when the solar system was still a shooting gallery of half-formed worlds, a body the size of Mars slammed into the young Earth at a glancing angle. The energy of the collision was almost incomprehensible. It liquefied both objects. It vaporized rock. It blasted a cloud of molten debris into orbit around the wounded Earth. And from that cloud, over a period of months or years, the moon condensed. The hypothesis was elegant. It explained why the moon has almost no iron core. The impactor's core merged with Earth's, so the debris cloud was mostly mantle material, light silicate rock. It explained the moon's lack of volatile elements. The heat of the collision boiled them away. It explained the angular momentum of the Earth-Moon system, at least roughly, and it explained why the moon orbits in the same plane as the Earth's equator, rather than the plane of the solar system. The theory was so clean that by 1984, at a landmark conference in Kona, Hawaii, the planetary science community adopted it as the standard model. The impactor was given a name, Theia, after the Greek titan who was the mother of Selene, the goddess of the moon. For 20 years, the giant impact hypothesis sat comfortably at the center of lunar science. Textbooks printed it as fact. Documentaries animated it with sweeping CGI. If you Google how the moon formed right now, the first result will tell you about Theia. And for a long time, it was enough. The numbers were close, the physics was plausible, the story was satisfying. But science does not run on satisfaction. It runs on precision. And when the precision improved, the story started to crack. The first crack was mechanical. In any collision, momentum is conserved. The total amount of spin in the system before the impact must equal the total spin after. You can redistribute it, transfer it from one body to another, but you cannot create or destroy it. This is not a theory. It is a law. When Robin Canup, one of the leading modelers of planetary collisions, ran high-resolution simulations of the Theia impact in 2012, she found that the standard scenario, a Mars-sized body hitting Earth at a glancing angle, produced a moon with approximately the right mass, but the wrong spin. The Earth-Moon system as it exists today does not rotate fast enough. The angular momentum is too low. If the impact happened the way the textbooks describe it, the Earth should be spinning faster than it does, and the moon should be orbiting closer than it does. The numbers do not close. Canup tried to fix it. She adjusted the mass of Theia. She changed the angle of impact. She altered the speed. She ran hundreds of simulations, tweaking variables until she found a narrow set of conditions that reproduced the current angular momentum. The fix worked on paper, but the conditions it required were so specific, so finely tuned, that the model lost its original appeal. The beauty of the giant impact hypothesis was that it was robust. Any large impactor at any reasonable angle would produce something like the moon. Canup's correction turned it into a precision shot. One particular mass, one particular angle, one particular velocity. If any of these were slightly different, you get a different outcome. The model went from being an explanation to being a coincidence. And coincidences in science are not answers. They are flags. They are signals that you have tuned your model to fit the data instead of letting the data reveal the mechanism. The foundation held, but the foundation was now made of assumptions you could not verify. That is not bedrock. That is a flaw you are choosing not to look under. The second crack came from chemistry, And it was worse. In 2001, a team led by Eirik Wiechert at the University of Göttingen measured the oxygen isotope ratios of lunar samples brought back by the Apollo missions. Oxygen comes in several isotopes, atoms with the same number of protons but different numbers of neutrons. The ratio between these isotopes is like a fingerprint. Every body in the solar system has a slightly different ratio, because each body formed from a slightly different mix of primordial material. Mars has its own oxygen fingerprint. Meteorites from the asteroid belt have theirs. Earth has its own. And the Moon, if it contains material from Theia, should have a fingerprint that is a blend of Earth and Theia, measurably different from Earth alone. It does not. The oxygen isotopes of the Moon and the Earth are identical, not similar, not close, identical within the margin of measurement error. This result landed like a grenade in the middle of the giant impact community. If Theia was a separate body that formed in a different part of the solar system, it should have carried its own isotopic signature. The collision should have mixed two different fingerprints together, and the Moon should show the blend. It does not show a blend. It shows pure Earth. There are only two ways to explain this. Either Theia formed from exactly the same material as Earth, in exactly the same orbit, with exactly the same isotopic composition, which is statistically almost impossible given what we know about how planets form. Or the impact was so violent that it completely homogenized both bodies, mixed every atom of Theia with every atom of Earth, until no trace of the original difference survived. But if that happened, if the mixing was total, then you have a new problem. Total mixing should produce a uniform moon. A moon with the same composition everywhere. The same crust on both sides. The same chemistry in both hemispheres. You should not get a body where one half is enriched in KREEP and the other is barren. You should not get a 40-kilometer asymmetry in crustal thickness. The explanation that saves the chemistry destroys the structure. And the structure is what started this entire investigation. The circle is tightening. In 2018, two scientists at Harvard tried to save the model. Sarah Stewart and Simon Locke proposed a radical revision of the giant impact. Their version did not produce a debris disk. It produced something far stranger, a structure they called a synestia. In their simulation, the collision between Theia and Earth was so energetic that it did not just melt both bodies, it vaporized them. The entire mass of Earth and Theia merged into a single rotating cloud of superheated silicate vapor, a swollen donut-shaped object thousands of kilometers across, spinning fast enough to flatten itself into a torus. The Moon did not form from chunks of debris raining down into a disk. It condensed inside the vapor cloud itself, like a raindrop forming inside a thunderstorm. The advantage of this model is real. If both bodies were fully vaporized and mixed at the atomic level, the isotopic fingerprints would homogenize. Earth and Moon would end up with identical oxygen signatures, which is exactly what Wiechert measured. The synestia model solves the chemistry, but it creates a new problem. A vapor cloud hot enough to homogenize isotopes is hot enough to drive off volatile elements: water, sodium, potassium. Anything with a low boiling point should have been lost to space. The Moon that condenses from a synestia should be bone dry. In 2008, Alberto Sal and his team at Brown University analyzed tiny glass beads trapped inside Apollo basalt samples. These beads formed deep inside the Moon from ancient volcanic eruptions. Sealed inside the glass, preserved for billions of years, was water. Not much by terrestrial standards, but far more than a synestia model predicts. The Moon is not dry. It has water locked in its interior. The model that explains the isotopes cannot explain the water. The model that explains the water cannot explain the isotopes. And neither model explains the crustal asymmetry, the KREEP distribution, or the gravity anomalies. Every attempt to patch one hole rips open another. The origin of the Moon is not an unsolved problem in the way that dark matter is unsolved. Dark matter is a mystery about something far away. The origin of the Moon is an unsolved problem about an object you can see from your kitchen window. We do not know how it was born, but there is one place where the universe has done some of the work for us. One place where the crust has been torn open so deeply that whatever lies beneath should be exposed. The South Pole-Aitken basin is a wound. It sits on the far side of the moon, centered near the lunar South Pole, and it is the largest confirmed impact structure in the solar system. 2,500 kilometers from rim to rim, 8 kilometers deep at its lowest point. The object that created it struck the moon with enough force to excavate a volume of rock larger than the entire state of Texas stacked 100 kilometers high. The basin was first identified by Deborah Stewart Alexander and Keith Howard in 1970, working from early orbital photographs. But it took decades of additional mapping to reveal its true scale. It is so large that standing inside it, you would not know you were in a crater. The walls curve away beyond the horizon. The floor is an entire landscape of secondary craters and fractured bedrock. At 8 kilometers deep, the impact should have punched clean through the crust. Remember the numbers. The far side crust averages 100 kilometers thick, but that is the average. In the center of South Pole-Aitken, the crust has been thinned dramatically. Models of the impact predict that the excavation reached deep enough to expose the mantle, the layer of dense rock that sits between the crust and the core. If true, this is extraordinary. The mantle of the moon is the one thing we have never directly sampled. Every piece of rock the Apollo astronauts brought back came from the crust. Every measurement we have of the interior is indirect, inferred from gravity and seismic waves, never touched. South Pole-Aitken should be the window, the one place where the universe cracked the shell hard enough to let us see inside. All you have to do is land there, scoop up the dirt, and analyze it. In January 2019, that is exactly what happened. On January 3rd, 2019, the Chinese spacecraft Chang'e 4 touched down inside Von Karman crater, a 186-kilometer wide impact basin nested within the floor of South Pole-Aitken. It was the first time in history that anything had landed on the far side of the moon. Communication with Earth was impossible directly, since the far side never faces our planet. So the Chinese Space Agency had pre-positioned a relay satellite called Queqiao at the L2 Lagrange point behind the moon to bounce signals back and forth. The lander carried a small rover named Yutu-2. U2 rolled off the platform and onto the surface of the deepest basin in the solar system. Its spectrometers began analyzing the soil. The expectation was clear. At this depth, after an impact this violent, the regolith should contain minerals from the mantle: olivine, pyroxene, rich in magnesium, dense, heavy greenish rock that forms under extreme pressure deep inside a planetary body. That is what every model predicted. That is what the scientists were looking for. In May 2019, Chunlai Li and his colleagues published the results in Nature. The soil contained some olivine, but far less than expected. The dominant minerals were low calcium pyroxene and plagioclases, materials associated with the crust, not the mantle. 8 kilometers of excavation. The most violent impact in the solar system's recorded history. And the floor of the wound still looks like crust. Either the mantle is not what we modeled it to be, which means our understanding of the moon's bulk composition is wrong. Or the impact did not penetrate as deep as the physics demands, which means our understanding of impact mechanics at this scale is wrong. Or there is a third option that nobody wants to write in a paper. Maybe there is something between the crust and the mantle that we have not accounted for. Something that absorbed the blow and sealed the wound from below. Whatever the answer is, the window that was supposed to let us see inside the moon turned out to be a mirror. We looked in and saw our own assumptions staring back. But the surface was not the only surprise waiting at South Pole-Aitken. While Yutu-2 was crawling across the regolith, analyzing minerals that should not have been there, a team led by Peter James at Baylor University was looking at the same basin from a completely different angle. Not from the surface down, but from orbit, using the GRAIL gravity data. James and his colleagues were mapping the gravitational field beneath the basin floor with extreme precision, looking for density variations that might reveal what the impact had done to the deep structure of the crust and upper mantle. What they found was published in the journal Geophysical Research Letters in June 2019, 5 months after Chang'e 4 landed. Beneath the floor of South Pole-Aitken, buried hundreds of kilometers below the surface, sits an anomalous mass, not a small one. James estimated it at roughly 2.18 times 10 to the 18th kilograms. That is a number that does not mean much until you put it in context. It is approximately 5 times the mass of the big island of Hawaii. All of it concentrated in a single region beneath the largest impact scar in the solar system. The mass is too large and too localized to be a normal density variation in the mantle. Something specific is down there. The leading hypothesis is that it is the metallic core of the impactor itself, the asteroid or protoplanet that carved the basin billions of years ago. The idea is that the core of the impactor punched through the crust, sank into the upper mantle, and stayed there. A dense iron-nickel lump embedded in the body of the moon like a bullet lodged in muscle. The hypothesis is reasonable, but it does not explain why the surface above it shows no mantle material. If a metallic core sank through the crust, it should have dragged mantle rock upward in its wake. That rock should be on the surface. Chang'e 4 did not find it. So you have a basin where the top does not show what the models predict, and the bottom contains a mass that the models cannot fully explain. The deepest wound on the moon, and it gives you 2 mysteries instead of 1 answer. If looking at the surface does not work, and looking through the gravity field only reveals more questions, there is one method left. One way to understand what a body is made of from the inside out. You hit it and listen to how it rings. Seismology is the only direct method we have for reading the interior of a planetary body. Not orbital spectroscopy, which can only see the top few millimeters of soil. Not gravity mapping, which tells you where mass is concentrated, but not what it is made of. Not radar, which penetrates the crust, but fades before it reaches the mantle. Seismology listens to vibrations. When something strikes a planet or when its interior shifts under tidal stress, waves propagate outward through the body. The speed and direction of those waves depend on what they pass through. Dense rock transmits them faster. Liquid slows them down or blocks them entirely. A cavity reflects them back. By placing seismometers on the surface and recording how the waves arrive, you can reconstruct the interior structure the way a doctor reads an ultrasound. You do not need to drill. You do not need to see. You just need to listen. On Earth, seismology has mapped the planet's interior with extraordinary precision. We know the radius of the core to within a few kilometers. We know where the mantle transitions from solid to partially molten. We know the thickness of tectonic plates, all of it from listening. For the moon, seismology should have been the skeleton key. One good network of instruments, a few years of data, and the interior would reveal itself. We built that network. It was called the Apollo Lunar Surface Experiments Package, ALSEP. Between 1969 and 1972, Apollo astronauts deployed seismometers at 5 locations on the near side of the moon. The instruments were sensitive, well calibrated, and designed to operate for years. They worked. They recorded thousands of events, moonquakes, thermal cracking, meteorite impacts, and one of the very first things they recorded was something that nobody had predicted, and that nobody has fully explained since. On November 20th, 1969, the crew of Apollo 12 deliberately crashed their spent lunar module ascent stage into the surface of the moon. The impact point was 72 kilometers from the seismometer they had planted hours earlier. The instrument was built by a team led by Gary Latham at the Lamont Doherty Earth Observatory. It was designed to detect natural moonquakes. Nobody knew exactly what a deliberate impact would look like on the seismogram. On Earth, when you hit the ground with a large object, the seismic signal is sharp. A spike of energy followed by a rapid decay. The ground absorbs the vibration quickly because it is full of water, cracks, and heterogeneous material that scatter and dampen the waves. The signal from the Apollo 12 impact did not behave like that. The seismometer recorded a signal that started small, built slowly to a peak, and then decayed with agonizing slowness. The moon rang for 55 minutes, not a sharp ping. A sustained, reverberating hum, like a tuning fork the size of a continent. Latham described it as astonishing. The waveform looked nothing like anything recorded on Earth. On our planet, seismic energy dissipates in minutes. The moon held onto it for nearly an hour, passing the vibration back and forth through its body as if it did not want to let go. The standard explanation is that the moon's outermost layer, the regolith and fractured megaregolith, is extremely dry. On Earth, water in rock acts as a damper. It absorbs vibrational energy and converts it to heat. The moon has no liquid water in its crust, so the waves bounce around with almost nothing to absorb them. It is a plausible explanation. It accounts for the slow buildup and the extended ringing, but it only accounts for the crust, the outermost skin. If the anomalous ringing were purely a surface effect, then a stronger impact should produce a proportionally longer signal. A linear relationship. Hit harder, ring longer, but by the same ratio. That is not what happened next. On April 15th, 1970, the third stage booster of Apollo 13, the S-4B, was deliberately steered into the lunar surface. The mission itself had already become a survival story. An oxygen tank had exploded on the way to the moon, and the crew was limping home in the lunar module, using it as a lifeboat. But the booster had been released before the explosion, and it followed its programmed trajectory into the moon. The impact was 4 times more energetic than the Apollo 12 ascent stage crash. 4 times the mass, 4 times the kinetic energy slamming into rock at roughly 2.5 kilometers per second. If the ringing were a surface effect, a quirk of dry regolith scattering waves, the signal should have been proportionally longer. 4 times the energy, maybe 4 times the duration, maybe 5. A linear scaling. The seismometers recorded a vibration that lasted more than 3 hours, not 4 times longer than 55 minutes. Roughly 3.5 times longer, but with a shape that was qualitatively different. The waveform was broader, the buildup was slower, the peak was lower relative to the total energy input. The decay stretched out in a way that the surface scattering model struggled to reproduce. Hit the moon harder and it does not just ring louder, it rings differently. The character of the response changes. That is not what happens when you're dealing with a surface layer. If you tap a wine glass gently, it rings at a certain pitch. If you tap it harder, it rings louder at the same pitch. The pitch does not change because the pitch is a property of the glass, not the tap. But if you fill the glass with sand, or if you crack it, the pitch shifts. The response changes because the structure has changed. On the moon, the structure did not change between the 2 impacts. The same body was hit in 2 different places with 2 different energies. And the response was not a simple scaling. It was a different signature. Something inside the moon was shaping the waveform. Something deeper than the regolith. Something that the simple dry crust model did not account for. The data sat in the archives. It was not wrong. It was not noisy. It was just uncomfortable. And the next set of data from those same instruments would be even more uncomfortable. The ALSEP seismometers did not just record impacts. They listened continuously for years, picking up every vibration that passed through the lunar interior. Most of what they heard was thermal cracking, the surface expanding and contracting as it cycled between the scorching heat of lunar day and the freezing cold of lunar night. That was expected. Some of what they heard was meteorite impacts, small rocks slamming into the far side and sending waves through the body. That was expected too. But buried in the data was a third category of signal that was neither surface noise nor external impact. Deep moonquakes, faint, repetitive seismic events originating from sources 700 to 1,100 kilometers below the surface, deep inside the moon, far below the crust, in a region that by all models should be hot, plastic, and quiet. In 2005, Yosio Nakamura at the University of Texas reanalyzed the entire ALSEP seismic catalog using modern computational methods. He identified 28 distinct nests of deep moonquakes, each one a localized source that fired repeatedly over the 8 years of recording. The events were tidal in nature. The moon's interior flexes as it moves closer to and farther from the Earth during its elliptical orbit, and this flexing generates stress that releases a seismic energy. That part made sense. What did not make sense was the timing. Tidal stress follows a predictable cycle. It is governed by the moon's orbital period, 27.3 days, and the geometry of the orbit is known with extreme precision. You can calculate exactly when the tidal force peaks. The deep moonquakes should fire at those peaks. They do not. Some nests fire near the predicted tidal maximum. Others fire days before or days after. Some fire at intervals that do not correspond to any simple harmonic of the orbit. Nakamura found that the timing pattern could not be fully explained by tidal mechanics alone. Something inside the moon was modulating the signal. Some internal property, a structural feature, a thermal gradient, a compositional boundary was altering when and where the stress released. The moon shakes on a schedule, and the schedule is written in a language we have not learned to read. And then we stopped listening. The Apollo lunar surface experiments package was designed to run for at least a year after each mission. It exceeded expectations. The seismometers kept transmitting through the mid-1970s, sending data back to Earth via a direct radio link. By 1977, the stations were still functional, still recording, still picking up deep moonquakes and surface events, and the occasional meteorite strike. But NASA had a problem that had nothing to do with the moon. The budget was shrinking. The Vietnam War had drained federal spending. The public had lost interest in Apollo the moment the last astronaut left the surface. The agency was pivoting toward the space shuttle, a new program that consumed every available dollar. On September 30th, 1977, NASA sent the shutdown command. Every ALSEP station on the moon went silent. Not because the instruments had failed, not because the data had answered the questions, not because someone reviewed the seismic catalog and concluded that the interior was well understood. They turned it off because it cost money to keep the receiving stations on Earth operational, and the money was needed elsewhere. Imagine you were a doctor examining a patient with symptoms you have never seen before. The heartbeat is irregular. The bones ring when you tap them. The chemistry of the left side does not match the right. You hook the patient up to a monitor. For 8 years, the monitor records data that you cannot fully interpret. Strange rhythms, deep pulses on a schedule that does not match your textbooks. Then, the hospital administrator walks in and unplugs the monitor. Not because the patient is cured, because the electricity bill is due. That is what happened with the moon. In 2011, Renee Weber and her team at NASA Marshall published the best available model of the lunar core. Partial melt at the base of the mantle. A small fluid outer core. A solid inner core. The model was built entirely from Apollo-era data. Sensors designed in the 1960s. Data recorded on magnetic tape. We are trying to understand the interior of the object closest to Earth using instruments that a person born in 1977 has never seen operational. We did not stop because we understood. We stopped because we forgot to care. And while we were not listening, the moon kept talking. For 400 years, people have been seeing things on the moon that should not be there. Flashes of light, temporary hazes, patches of color that appear over a crater, linger for hours, and then vanish. Astronomers call them transient lunar phenomena, TLP. The reports go back to at least 1540, when observers noted a strange glow near the crater Aristarchus. Over the centuries, sightings accumulated. professional astronomers with large telescopes, amateur observers with meticulous notebooks. The events were always brief, always localized, and always impossible to predict. Some described a reddish haze hanging over a crater rim. Others saw a sharp white flash, like a spark, in a region where no meteorite impact was recorded. Others noted that a familiar feature temporarily changed color or brightness for no apparent reason. In 1968, Barbara Middlehurst, a researcher at the University of Arizona, compiled all known reports into a single document for NASA. Technical Report R-277. 579 events spanning more than 4 centuries. The catalogue was not a collection of folklore. It was a systematic aggregation of observations made by trained observers using calibrated instruments, and it posed a problem that lunar science did not want to deal with. The moon is officially classified as geologically dead. It has no atmosphere, no plate tectonics, no volcanic activity. Its interior cooled billions of years ago, or so the standard model insists. A dead body does not glow. A dead body does not exhale gas. A dead body does not flash with light in the same spot over and over across centuries. And yet, the catalogue existed. 579 times, someone looked at the moon and saw it do something that a dead world is not supposed to do. The scientific community's response was predictable. The observations were dismissed as atmospheric artifacts, optical illusions caused by turbulence in Earth's atmosphere distorting the image, temperature effects on telescope optics, overactive imaginations. The explanations were reasonable enough to justify moving on, but they were never tested against the data. Nobody ran a systematic analysis to check whether the reported locations correlated with any known geological feature. Nobody checked whether the timing of events correlated with any known physical process. The catalogue was filed and forgotten, until someone looked at it from above. In 1958, 11 years before the Apollo landings, a Soviet astronomer named Nikolai Kozyrev pointed the 50-inch reflector at the Crimean Astrophysical Observatory at the crater Aristarchus. Aristarchus is the brightest feature on the lunar surface, a 40-kilometer wide impact crater on the near side that reflects more light than any other spot on the moon. It is also the single most active location in the TLP catalogue. More sightings have been reported at Aristarchus than at any other feature. Kozyrev was not looking for transient phenomena. He was taking routine spectrograms of the lunar surface, breaking the reflected sunlight into its component wavelengths to study the mineral composition. What he recorded that night was an anomaly. The spectrum showed emission bands that did not belong to reflected sunlight. They indicated the presence of gaseous molecules above the surface, specifically carbon-bearing compounds. Kozyrev interpreted this as evidence of outgassing, volcanic gas escaping from the interior of the moon through fractures in the crust. The reaction from the scientific establishment was hostile. The moon was supposed to be dead. Kozyrev's data was picked apart, questioned, and for decades treated as an unreliable outlier. He was a controversial figure already, having spent years in Soviet labor camps before returning to astronomy, and his reputation made it easy to dismiss his results without fully engaging with the data. But data does not care about the reputation of the person who collected it. 40 years later, instruments in orbit around the moon began to confirm that something was happening at Aristarchus and at other TLP hotspots. The Lunar Prospector spacecraft, the same mission that mapped the creep distribution, carried an alpha particle spectrometer designed to detect radon gas. Radon is a decay product of uranium and thorium, elements present in the lunar interior. If the moon's crust is cracked and gas is escaping from below, radon should be detectable in trace amounts above the surface. The instrument found it, not everywhere but in localized patches, and the patches correlated with known TLP sites. Kozyrev had been right. Something was coming out of the moon. The question was, what was pushing it? The answer arrived in 2010, and it was not what anyone expected. Thomas Waters, a senior scientist at the Smithsonian, had been studying high-resolution images from the Lunar Reconnaissance Orbiter. LRO's cameras could resolve features as small as half a meter across. A level of detail that turned the moon from a smooth grey marble into a landscape of razor-sharp shadows and fine-textured geology. Waters was looking for a specific type of feature, Labatt scarps. These are low, curved ridges on the surface, typically a few tens of meters high and several kilometers long. On Earth, scarps form when tectonic forces compress the crust, pushing one block of rock up and over another along a thrust fault. They are signatures of a contracting body, a body that is cooling and shrinking. The moon should not have them. If the moon finished cooling billions of years ago, any scarps from that era would have been obliterated by meteorite impacts long since. The only way to find fresh scarps on the moon is if the moon is still shrinking. Waters found them, not a few, thousands, distributed across the entire surface, near side and far side, highlands and maria. And their morphology was sharp, crisp edges, undegraded slopes, minimal crater overprinting. By the standards of lunar geology, these features were young. Waters and his team estimated their age at less than 50 million years. Some could be less than a million. On a body 4.5 billion years old, that is not ancient history. That is yesterday afternoon. The moon is contracting right now. Its interior is still cooling, still losing heat, still shrinking by a tiny amount. And as it shrinks, the crust cracks. New faults form, old faults reactivate. The surface is breaking open in real time. A body that was supposed to be a frozen relic, a dead museum piece orbiting Earth since the age of the dinosaurs, is geologically active at this moment. And if the crust is cracking, then the cracks are pathways. Channels from the interior to the surface. Channels through which gas, heat, and whatever else is down there can find its way out. In 2005, Stephanie Lawson and her colleagues published a study that connected two datasets nobody had thought to compare. The first was the Lunar Prospector radon data, the sporadic detections of radioactive gas above the lunar surface that had quietly confirmed Kozyrev's observations decades earlier. The second was the TLP catalogue, Middlehurst's 579 events compiled in 1968. Lawson mapped the radon emission sites onto the same coordinate grid as the TLP reports. The overlap was not perfect, but it was far too strong to be coincidence. The regions where Lunar Prospector detected radon from orbit corresponded, at a statistically significant level, to the regions where observers on Earth had been reporting flashes and glows for centuries. The implication was straightforward. The moon is leaking. Gas from the interior, driven by residual radioactive decay or by the mechanical stress of tidal flexing and ongoing contraction, migrates upward through fractures in the crust and escapes into the vacuum above. When it reaches the surface, the gas may interact with solar radiation or with the charged particles of the solar wind, producing the brief optical events that observers had been recording since the Renaissance. The TLP reports were not hallucinations. They were not atmospheric artifacts. They were the visible signatures of a process happening inside the moon right now. 400 years of human observation, dismissed as noise, validated by a robot in orbit. The moon is not dead. It breathes. Not the way a living thing breathes, in rhythmic cycles of oxygen and carbon dioxide. It breathes the way a wounded body exhales, slowly, intermittently. Through cracks it cannot close. And that changes everything about the way you have to think about this object. The surface is asymmetric. The crust is chemically divided. The gravity field hides structures that the surface does not show. The origin model does not work. The deepest wound reveals neither mantle nor explanation. The interior rings when struck and shakes on a schedule nobody can decode. We stopped listening half a century ago, and the body that was supposed to be a cold, dead relic is exhaling gas through fresh cracks in its skin. This is what we know about the object closest to us in all of space. But maybe at least the orbit makes sense. Maybe the way it moves, the geometry of its path around Earth, follows a pattern that the physics can cleanly explain. It does not. Start with the most basic fact about the Moon's orbit, its size relative to the planet it circles. The Moon is 3,474 kilometers in diameter. Earth is 12,742. The ratio of their masses is roughly 1 to 81. In the context of the inner solar system, this is an anomaly so extreme that it deserves its own category. Look at Mars. It has two moons, Phobos and Deimos. Phobos is 22 kilometers across. Deimos is 12. They are captured asteroids, specks of rubble held in loose orbits around a planet 10,000 times their mass. Venus has no moon at all. Mercury has no moon. Every other rocky planet in the inner solar system either has no companion or has companions so small they are barely visible in a telescope. And then there is Earth, a middleweight rocky planet with a companion 1/4 its diameter and 1/80th its mass. If you showed an alien astronomer a lineup of the inner planets and asked which one has the anomalous satellite, they would point at Earth without hesitating. The Moon is not a captured asteroid. It is too big, too round, and too chemically similar to Earth to have been snagged from a passing orbit. It is not a co-formation twin, a body that condensed alongside Earth from the same cloud of dust. The chemistry rules that out because the Moon's iron content is far too low for a body that formed in the same neighborhood as Earth. And the giant impact model, the one mechanism that was supposed to explain the Moon's size, is cracking under the weight of its own contradictions, as we have already seen. The Moon is too large for its planet. That is not a poetic statement. It is a measurement. No standard formation pathway produces a satellite this size around a planet this small in the inner region of a solar system. You can model it after the fact, fit curves to the data, adjust parameters until the simulation outputs a body that resembles the Moon. But the models are not predictions, they are rationalizations. The Moon exists, so there must be a way it formed. That logic is valid, but it is not the same as the understanding. There is another number that sits uncomfortably at the center of lunar science, and it has nothing to do with chemistry or gravity. It has to do with geometry. The Moon is 400 times smaller than the Sun. The Sun is 400 times farther from Earth than the Moon. This means that from the surface of our planet, the apparent angular diameter of the Moon and the apparent angular diameter of the Sun are almost exactly the same, half a degree of arc. When the Moon passes between the Earth and the Sun, it covers the solar disk with a precision that looks engineered. The corona becomes visible. The chromosphere flares at the edges. The fit is so exact that for centuries, total solar eclipses were the only way to study the Sun's outer atmosphere. No other planet in the solar system has this. No other moon produces a total eclipse of the Sun where the apparent sizes match this closely. Mars cannot see a total eclipse. Jupiter cannot. Saturn cannot. Only Earth, with this specific moon at this specific distance. And the coincidence is temporary. Lunar laser ranging experiments, first conducted during the Apollo missions and continued with reflectors still sitting on the surface, have measured the Moon's recession rate at 3.82 centimeters per year. The Moon is drifting away, slowly but relentlessly. Billions of years ago, the Moon was much closer. It would have appeared far larger than the Sun in the sky, blocking it completely with room to spare. Billions of years from now, the Moon will be too far away to cover the Sun at all. Annular eclipses only, a ring of fire with no total darkness. We are living in the one window of Earth's history. A window perhaps a few 100 million years wide in a timeline of billions, where the angular sizes match. The odds of a technological civilization arising on this planet and developing the ability to observe the Sun's corona during the exact epoch when total eclipses are possible is a coincidence that no model of lunar formation was designed to produce. It simply is, and it is not the last coincidence. In 1993, Jacques Lascar at the Paris Observatory published a paper that redefined the moon's role in the solar system. Lascar was not a lunar scientist. He was a specialist in celestial mechanics, the mathematics of how orbits evolve over millions and billions of years. His work focused on a deceptively simple question: what keeps the Earth's axial tilt stable? The Earth is tilted at 23.4 degrees relative to its orbital plane. That tilt gives us seasons. Summer in the hemisphere that leans toward the sun, winter in the hemisphere that leans away. The tilt varies slightly over tens of thousands of years, wobbling between about 22 and 24.5 degrees, and these small wobbles are enough to trigger ice ages. But the range is narrow. The wobbles are gentle. The climate system can absorb them. Lascar ran simulations of what would happen if the moon did not exist. The results were catastrophic. Without the moon's gravitational stabilization, Earth's axial tilt would not wobble gently between 22 and 24 degrees. It would swing chaotically across a range of 0 to more than 60 degrees. At zero tilt, there are no seasons. The equator bakes, the poles freeze, weather patterns stagnate. At 60 degrees, the poles point nearly at the sun for half the year. Entire continents cycle between permanent daylight and permanent darkness every 6 months. Ice sheets advance and retreat across thousands of kilometers in geological blinks. No stable climate, no predictable agriculture, no long-term ecosystem that a complex biosphere can rely on. Mars has no large moon. Mars has an axial tilt that wanders chaotically, exactly as Lascar's model predicts. It swings from 15 to 45 degrees and possibly further over millions of years. Mars once had liquid water. It lost it. The connection is not proven, but it is suggestive. The moon does not just orbit the Earth. It holds the Earth in place. It is the gravitational anchor that keeps our planet's axis from tumbling. Without this specific object, at this specific mass, at this specific distance, the conditions for complex life on Earth's surface may not exist. The moon is not a companion. It is a prerequisite. And there is one more feature of the moon's behavior that ties this web of coincidences into a knot: the tidal lock. The moon rotates on its axis at exactly the same rate it orbits Earth. 1 rotation per revolution. This is why you have only ever seen one face. The mechanism behind tidal locking is well understood. It was described rigorously by Brad Gladman and his colleagues in 1996. When 2 bodies orbit each other, the gravitational pull of the larger body raises tidal bulges on the smaller one. These bulges create friction inside the smaller body. The friction dissipates rotational energy. Over time, the smaller body slows down until its rotation matches its orbital period. It locks, face to face, permanently. This happens to many moons in the solar system. Phobos is locked to Mars. Europa is locked to Jupiter. The physics is clean. But the speed at which locking occurs depends on a variable we do not have: the internal structure of the body. A rigid, uniform sphere locks slowly. A body with a liquid interior, or with a partially molten layer that amplifies tidal dissipation, locks fast. The rate depends on viscosity, on the distribution of mass inside the body, on the thermal state of the mantle. All the things we do not understand about the moon. So here is where the circle closes. We explain the orbit by pointing to the tidal lock. We explain the tidal lock by pointing to the internal structure. We explain the internal structure by pointing to the formation model. And the formation model does not work. Every answer in this chain is a reference to another question. And every question is a reference to a gap we have not filled. The orbit depends on the interior. The interior depends on the origin. The origin depends on a model that breaks under its own data. You're not climbing a ladder toward understanding. You're walking in a circle, and every lap the ground gets softer. When the logic of a system folds in on itself like this, when every variable points at another variable and none of them points at solid ground, there are people who start thinking outside the circle entirely. start with the most basic physical property of any object: its weight. The average density of the Moon is 3.34 grams per cubic centimeter. Earth's is 5.51. That gap is enormous. Earth is dense because it has a massive iron-nickel core that accounts for roughly 32% of the planet's total mass. Iron is heavy. It sank to the center during differentiation, the process by which a molten body sorts itself into layers. Heavy stuff in the middle, light stuff on top. The Moon, if it formed from Earth material via the giant impact, should have gone through the same process. It should have a proportionally significant iron core. It does not. The best estimates derived from the Apollo seismic data and refined by René Weber's 2011 model put the Moon's core at somewhere between 1 and 3% of its total mass. Tiny. Disproportionately small for a body 3,474 kilometers in diameter. This creates a problem that does not get enough attention. If the Moon formed from the same cloud of vaporized rock that included Earth material, and if that cloud contained a representative share of iron, where did the iron go? The Synestia model argues that the iron sank back into Earth before the Moon condensed. Possible. But then you need to explain how the condensation process separated the silicate so cleanly from the metal without leaving a measurable isotopic trace of that separation. Nobody has done that convincingly. The Moon is too light. Not by a small margin, by a structural margin. Its density is closer to that of the Earth's upper mantle than to the Earth as a whole. It is as if someone scooped the skin off the planet, the outermost rocky layer, and assembled it into a sphere without including any of the heavy material underneath. That image is uncomfortable because it sounds designed. It sounds like selection rather than accident. And that discomfort is exactly where two Soviet scientists found themselves in 1970, staring at the same numbers and reaching a conclusion that nobody wanted to hear. In July 1970, the Soviet popular science journal Sputnik published an article by two members of the Soviet Academy of Sciences. Their names were Michael Vasin and Alexander Sherbakov. The title, translated loosely, was "Is the Moon the Creation of Alien Intelligence?" The article proposed that the Moon is not a natural body. It argued that the anomalies, the low density, the thin metallic core, the bell-like ringing, the asymmetric crust, the impossible orbit, were not unsolved puzzles waiting for better models. They were features. The Moon, Vasin and Sherbakov wrote, could be an artificial structure, a hollow shell constructed by an advanced civilization and placed in orbit around Earth for purposes we cannot determine. The reaction from the scientific community was immediate and predictable. The article was not peer-reviewed. It was published in a popular magazine, not a journal. The language was speculative and the tone was sensational. Western scientists dismissed it as Soviet pseudoscience. Soviet scientists distanced themselves from it quietly. The hypothesis became a punchline, a shorthand for the kind of thinking that serious researchers do not engage in. And that dismissal was justified. The claim was extraordinary. The evidence was circumstantial. The logical leap from anomalous data to alien construction skipped every intermediate step that science requires. But here is what the dismissal buried. The data that Vasin and Sherbakov pointed to was real. The low density was measured. The small core was measured. The ringing was recorded by NASA instruments. The crustal asymmetry was mapped by NASA orbiters. The orbital coincidences were calculated by NASA scientists. None of that data has been retracted. None of it has been explained. The hypothesis was wrong in its conclusion, but it was not wrong in its observation. The data was bizarre enough that two credentialed scientists, working within one of the most rigorous scientific traditions on Earth, looked at it and could not find a natural explanation that satisfied them. That does not mean the Moon is artificial. It means the data is strange enough to push trained minds to the edge of what they consider possible. And the edge is where the interesting questions live. If the hollow moon hypothesis is wrong, and it almost certainly is, then the data it was based on still needs an explanation. And there is one measurement that sits at the exact midpoint between the conventional and the radical, refusing to commit to either side. The moment of inertia. Every rotating body has a moment of inertia, a value that describes how its mass is distributed relative to its axis of spin. If all the mass is concentrated at the center, the moment of inertia is low. If the mass is spread evenly throughout, it is high. For a perfectly uniform solid sphere, the normalized moment of inertia is 0.4. For Earth, with its dense iron core pulling mass toward the center, the value is 0.331. The Moon's value, measured through decades of laser ranging and orbital tracking, and most precisely reported by James Williams and his colleagues at JPL in 2014, is 0.3931. Almost 0.4, almost uniform. This number is a quiet bombshell. A body that formed through differentiation, that melted and separated into a dense core and a lighter mantle and an even lighter crust, should have a moment of inertia well below 0.4. Earth does, Mars does, every differentiated body in the solar system does. The Moon barely qualifies. Its mass is distributed almost as if it were the same stuff all the way through. Not hollow. The seismic data rules that out. There is material inside. But the material is arranged with a uniformity that differentiation should have destroyed. A body that melted should have sorted itself. Heavy to the center. Light to the outside. The Moon apparently did not sort very well. Or it sorted, and then something redistributed the mass. Or it never fully differentiated in the first place, which contradicts the giant impact model because a body born from a cloud of vaporized rock at thousands of degrees should differentiate completely. The moment of inertia does not prove anything radical. It does not confirm any fringe theory. What it does is sit there, one decimal place away from perfect uniformity, quietly contradicting every standard model of how this body should be structured inside. And after 30 bits of data, 30 layers of anomaly stacked on anomaly, that quiet contradiction starts to sound very loud. There is a moment in every investigation where you have to stop looking at the evidence and start looking at the investigator. We have spent this entire journey pointing instruments at the Moon. Lasers, spectrometers, seismometers, gravity sensors, cameras with half-meter resolution. Every decade, the instruments get better. Every decade, the anomalies get worse. The natural assumption is that the problem is the Moon. The Moon is strange. The Moon is complicated. The Moon refuses to be explained. But there is another possibility. And it is the one that scientists are least comfortable considering. Maybe the problem is us. Maybe the problem is the method. Every model of the Moon begins with assumptions. The giant impact assumes a specific type of collision. Thermal evolution models assume a specific initial distribution of radioactive elements. Gravity models assume a specific relationship between density and depth. Each assumption is reasonable in isolation. But when you stack them, when you build a tower of reasonable assumptions, and then compare the tower to the actual data, the tower does not match. And instead of questioning the assumptions, we adjust parameters. We add epicycles, we patch the model to fit the data point that broke it, and then we are surprised when the next data point breaks it again. This is not a failure of intelligence. It is a structural limitation of the method. Confirmation bias is not a character flaw, it is a feature of how human cognition works. You see what you expect to see. You weight the data that confirms your model more heavily than the data that contradicts it. And when the contradictions pile up, you do not abandon the model. You make it more complicated. The Moon might be the object that reveals this limitation most clearly. Not because it is the strangest body in the solar system, but because it is the closest. We have more data on the Moon than on any other world, and that data has not converged on an answer. It has diverged. More information has produced less understanding. If that pattern holds, if it is not a temporary gap waiting for a better model, but a fundamental property of the relationship between our instruments and this object, then the problem is not that we have not found the right explanation. The problem is that our method of explanation has a ceiling, and the moon is sitting exactly on that ceiling, staring down at us, which raises a question that belongs not to geology or physics, but to philosophy. If the method has a ceiling, what is above it? In 2003, a Swedish philosopher at Oxford University named Nick Bostrom published a paper that had nothing to do with the moon. It was called, "Are You Living in a Computer Simulation?" The paper was short, precise, and built on a single logical argument that has never been refuted. Bostrom did not claim that we live in a simulation. He did something more unsettling. He proved that one of three statements must be true, and there is no fourth option. Statement 1. Virtually all civilizations at our level of development go extinct before they acquire the computing power to simulate conscious beings. Statement 2. Virtually all civilizations that acquire that power choose not to run such simulations. Statement 3. We are almost certainly living inside a simulation right now. The logic is airtight. If civilizations survive, and if they run simulations, then the number of simulated realities vastly exceeds the number of base realities. If you are a conscious being, and you do not know which kind of reality you are in, the probability that you are in the simulated majority is overwhelming. You can escape the conclusion only by believing that civilizations always die before reaching that stage, or that they always choose not to simulate. If you reject both of those, door number 3 is the only one left open. This is not mysticism. It is not conspiracy. It is a probability argument built on the same statistical principles that physicists use to estimate the number of stars in the galaxy. And it has a direct bearing on the moon. If reality is a computation, then anomalies like the ones we have catalogued, asymmetries that no model explains, coincidences that no formation pathway predicts, data that gets worse with better instruments, stop being mysteries of nature. They become artifacts of architecture, glitches, rounding errors, boundaries where the resolution of the simulation meets the resolution of the observer. The moon does not need to be artificial for this to matter. If the substrate of reality is informational, then everything is artificial in a sense. And the question shifts from what is the moon to what is the system that generates the moon. That question sounds like science fiction until you look at what physicists have actually been saying for decades. In 1990, John Archibald Wheeler, one of the most influential physicists of the 20th century, the man who coined the term black hole, summarized his life's work in 3 words: it from bit. His claim was radical and precise. Every physical quantity, every particle, every force, every field derives its existence from binary choices, from information. Matter is not the foundation of reality. Information is. The universe does not contain information. The universe is information. Wheeler was not a fringe thinker. He was Richard Feynman's doctoral advisor. He worked on the Manhattan Project. He spent decades at Princeton. When he said that physics is ultimately about information, the physics community listened. And in the years since, the idea has gained traction from unexpected directions. In 2010, Erik Verlinde at the University of Amsterdam published a paper arguing that gravity is not a fundamental force. It is an emergent phenomenon, a macroscopic effect that arises from the statistical behavior of microscopic information on a boundary surface. The math was rigorous. The implications were staggering. If gravity is not fundamental, but emergent, if it is a consequence of information processing rather than a cause, then the structure of spacetime itself is a readout, a display generated by deeper computational rules that we do not yet see. Now apply this lens to the moon. Every anomaly we have catalogued is a discrepancy between what our models predict and what reality shows. If reality is a computation, those discrepancies are not failures of our models. They are places where our models bump against the architecture of the computation itself. The moon's crustal asymmetry, its impossible chemistry, its gravity anomalies, its orbital coincidences, all of them could be the equivalent of texture seams in a rendered environment. Not errors in nature, errors in rendering. The moon is not broken. The simulation is showing its edges. That is an extraordinary claim. And extraordinary claims require not just arguments, but tests. In 2012, 3 physicists at the University of Washington proposed one. Silas Bean, Zohre Davoudi, and Martin Savage asked a simple question. If the universe is a simulation running on a discrete lattice, a grid of finite resolution rather than a smooth, continuous fabric, what observable consequences would that produce? The answer was specific. A discrete lattice imposes a maximum energy for particles moving through it. Think of a screen with pixels. If you zoom in far enough, the smooth image breaks into a grid. The grid has a smallest unit. Nothing smaller than 1 pixel can exist on that screen. In a lattice universe, the smallest unit would show up in the behavior of ultra-high energy cosmic rays, particles that slam into Earth's atmosphere at energies near the theoretical maximum. If space-time is continuous, these particles should arrive from every direction equally. If space-time is a lattice, the grid would impose a subtle directional preference. The particles would favor certain angles over others, the way light passing through a crystal bends along the crystal's axis. Bean and his colleagues calculated what the signature would look like and proposed that existing cosmic ray observatories could test for it. The Pierre Auger Observatory in Argentina, the Telescope Array in Utah, instruments that already collect this data. The test is real. The prediction is specific. The experiment is feasible. For the first time, the simulation hypothesis crossed the line from philosophy to physics. It became falsifiable. But here is where the story does not deliver the clean ending you might want. The data from cosmic ray observatories has shown some anisotropy, some directional preference, but the results are ambiguous. The signal is not strong enough to confirm the lattice hypothesis, and not absent enough to rule it out. We are standing at the edge of a test that could answer the deepest question a conscious being can ask: whether reality itself is fundamental or generated. And the answer so far is we cannot tell yet. The instrument is not quite sharp enough. The data is not quite clean enough. The resolution of our measurement is bumping against the resolution of what we are trying to measure. And if that sounds familiar, it should. It is the same pattern. Better instruments, more data, less clarity. The same spiral that has defined every layer of this investigation, from the first photograph of the far side to this moment. There is a word for the place where we are standing. It was defined in 1934 by a philosopher named Karl Popper, and it is the single most important boundary line in the history of science: falsifiability. Popper argued that the difference between science and everything else is not truth, it is testability. A statement is scientific if and only if there exists an observation that could prove it wrong. If no possible experiment can disprove your claim is not science. It is something else. It might be philosophy. It might be mathematics. It might be theology. It might even be correct. But it is not science, because science is defined by its willingness to be wrong. The simulation hypothesis sits exactly on this line. Bean's lattice test pushes it toward the scientific side. If the test finds the predicted anisotropy, the hypothesis gains ground. If it does not, the hypothesis does not die, because a more sophisticated simulation could use a non-lattice architecture that leaves no trace. The hypothesis retreats back across the line into philosophy, immune to disproof, unfalsifiable in Popper's strict sense. And here is the discomfort. Unfalsifiable does not mean false. It means unreachable. It means the method cannot touch it. The scientific method is the most powerful tool humanity has ever invented for understanding reality. It put people on the moon. It mapped the gravity field of a body 384,000 kilometers away to the precision of a micron. But it operates within boundaries. It can only investigate things that can be measured, tested, and potentially disproven. If there is something beyond those boundaries, science cannot see it. Not because it is not there, because the flashlight only reaches so far. The moon might be the object that marks the edge of the beam. One side of it sits in the light. We can measure the crust, we can map the gravity, we can analyze the chemistry. The other side sits in darkness, not the darkness of space, the darkness of the unmeasurable, the place where data stops producing understanding and starts producing only more questions. We have walked a long path to reach this wall. 40 layers of evidence, 60 years of missions, and the wall is not an answer. It is the place where answers stop. But we are not done. Because in the middle of all this uncertainty, one thing is happening that is not theoretical, not philosophical, not speculative. It is mechanical. It has a launch date, and it is pointed at the moon. The spacecraft is called Orion. It will sit on top of the Space Launch System, the most powerful rocket NASA has built since the Saturn V that carried Apollo astronauts half a century ago. Inside the capsule, 4 people: Commander Reed Wiseman, pilot Victor Glover, mission specialist Christina Koch, and Jeremy Hansen. Hansen is Canadian, the first non-American assigned to a lunar mission. Their trajectory will take them farther from Earth than any human being has traveled since 1972. They will loop around the moon, passing behind the far side, out of radio contact with Earth for approximately 30 minutes as the moon's body blocks all signals. During that half hour, they will be more isolated than any human in history. No communication with mission control, no communication with anyone. Just 4 people, a capsule, and the far side of the moon outside the window. The far side that Lunar 3 photographed in grainy black and white in 1959. The far side that GRAIL mapped in gravitational detail in 2012. The far side that Chang'e 4 touched for the first time in 2019. The far side that has accumulated more anomalies per square kilometer than any surface in the solar system. For 30 minutes, human eyes will look at it directly. Not through a camera feed, not through processed data, through glass. The mission is a test flight. Its primary objective is to verify that Orion's life support, heat shield, and navigation systems work for a crewed, deep space journey. It is engineering, not science. The crew will not land. They will not collect samples. They will not deploy instruments. They will fly around the moon and come home. But Artemis II is not the end. It is the rehearsal. And what comes after the rehearsal is what matters. Artemis III is designed to put boots on the surface. The landing site is the lunar South Pole, the rim of the same region where South Pole-Aitken basin carved its wound billions of years ago. The mission will carry instruments that did not exist during Apollo. The Farside Seismic Suite, a compact seismometer package designed to operate autonomously on the far side of the moon, powered by solar panels and communicating through relay satellites. For the first time since 1977, the moon will have ears. Not on the near side, where Apollo listened. On the far side, where no seismometer has ever been placed. The data it collects will pass through the region of the deep moonquakes that Nakamura identified. The ones firing on a schedule that tidal models cannot explain. If the signal is real, if the anomalous timing pattern persists in data collected by modern digital instruments instead of 1970s analog hardware, it will be very difficult to dismiss as an artifact. Artemis will also carry spectrometers capable of analyzing regolith composition at the molecular level. If there is mantle material exposed anywhere near the South Pole-Aitken rim, these instruments will find it. If the composition confirms what Chang'e 4 measured, that the expected mantle minerals are not where the models say they should be, the problem moves from ambiguous to confirmed. And the GRAIL follow-on concepts, next-generation gravity mappers with even higher resolution, are already in development. More precise measurements of the mass anomaly beneath SPA. Sharper images of the linear structures Andrews Hanna found on the far side. Every instrument on the list is designed to answer a specific question that this investigation has raised. The seismic network asks what the interior is made of. The spectrometers ask what the deepest wound contains. The gravity mappers ask what is hiding beneath the crust. The tools exist, the questions are defined. The launch dates are on the calendar. And this is the moment where the spiral either breaks or tightens. Because every previous instrument made the picture worse, every previous mission added complexity instead of clarity. Step back, look at the timeline. In 1959, Lunar 3 sent back the first photographs of the far side. Scientists saw a hemisphere that did not match the near side. They called it an anomaly and assumed that better data would explain it. In 1968, Muller and Sjögren discovered mascons, hidden masses beneath the surface that no model predicted. They called them a puzzle and assumed that better instruments would resolve it. In 1969, Apollo 12 hit the moon and it rang for an hour. The seismologists called it unusual and assumed that deeper analysis would clarify the mechanism. In 1998, Lunar Prospector mapped the KREEP distribution and found it concentrated on one hemisphere. Geochemists called it unexpected and assumed that thermal models would account for it. In 2001, Weichert measured identical oxygen isotopes in Earth and Moon rocks. Cosmochemists called it surprising and assumed that new formation models would accommodate it. In 2012, GRAIL mapped the gravity field with unprecedented precision and found more anomalies, not fewer. Geophysicists called it complex and assumed that the next mission would simplify the picture. In 2019, Chang'e 4 landed in the deepest basin in the solar system and did not find the mantle material that every model predicted. Planetary scientists called it puzzling and assumed that further sampling would resolve the discrepancy. Do you see the pattern? Every decade, the instruments get sharper. Every decade, the data gets richer. Every decade, the understanding gets worse. This is not a string of bad luck. This is not a sequence of temporary gaps waiting to be filled by the next clever graduate student. This is a 60-year trend with no inflection point. The curve does not bend toward resolution. It bends away from it. What if the spiral is not a flaw in our approach? What if it is a property of the object? What if the moon is the kind of thing that becomes less comprehensible the closer you look? Not because it is hiding something, but because its nature is incompatible with the resolution of the tools we use to look. A wall that recedes at exactly the speed you approach it. You never hit it. You never stop approaching. And the gap between you and understanding remains constant no matter how fast you run. That is what 60 years of lunar science looks like when you plot it on a graph. The line does not converge. It does not diverge wildly. It holds steady at a distance that feels close enough to keep you chasing, and far enough to never let you arrive. That is what hangs above you every night. Not a dead rock. Not an alien artifact. Not a glitch in a simulation. Something worse. An object that your species has touched, walked on, hammered, listened to, mapped to the centimeter, and still does not understand. 384,000 kilometers away. Close enough to see with your naked eye. But you are here. That is the part that matters now. You have walked through 60 years of data, through crustal asymmetries and gravity ghosts, and a bell that rang for an hour, and a wound that would not show its insides. You followed the spiral all the way down, past the models that broke, past the instruments that made things worse, past the edge where science hands you off to philosophy and philosophy hands you off to silence. And you are still here. The moon will be there tonight. Go outside and look at it. It will look the same as it always has. A pale disk in the sky, familiar as a streetlight, ordinary as a clock face. But you know now what it took 60 years of missions to learn. That thing is not ordinary. It is not understood. It may not be understandable, not fully, not with the tools your species currently has. And that is fine, because the point was never the answer. The point was the looking. The point was that you, a living thing standing on a rock that spins around a star in an unremarkable arm of an average galaxy, had the nerve to point a laser at the closest object in the sky and demand that it explain itself. It did not explain itself. It never has. But you asked. And asking is the thing that separates you from every silent rock in the solar system. The moon does not ask questions. You do. That is the difference between you and everything else in the night sky. Go outside, look up, let it be strange. You have earned that.